Hi, hello. Today I am going to explain about set theoretic properties. So in the last video, I'll explain about the closure properties of regular language. The same is continued in this. We already discussed about the closure properties of union, intersection, complement, clean closure, homomorphism, inverse homomorphism. So these are all some closure properties of regular language. The same thing is continued here in set theoretic properties. So here these are all the some properties, basic properties: union, intersection, complement, difference, and symmetric difference. So the first property is union. If L1 and L2 are regular, then L1 union L2 is also a regular language. Already we know about that in the closure properties of regular language. If L1 is a regular language and L2 is also a regular language, then union of L1 and L2 is also a regular language. So a new NFA can be constructed from the simultaneous both simulates both L1 and L2 in parallel in union theoretic properties. Similarly, in intersection, if L1 is a regular language and L2 is a regular language, then L1 intersection L2 is also a regular language. Here it can be implemented using the product construction, that is cross product of DFA method. Next one is complement. If L is a regular, then L dash is also a regular here. If we have a DFA for L, changing accepting states to non-accepting state and non-accepting state to accepting states, it's give you a DFA for its complement. uh, Difference. So up to this already we discussed in this closure properties of regular language. So that's the reason I didn't give any explanation for this. So in the difference, L1 and L2 are regular. Then L1 minus L2 is also a regular here. So first we have to know about the difference. If L1 is one regular language and L2 is one regular language, that means, for example, if L1 contain 1, 2, 3, 4, these elements, and L2 contains only 3, 4 means, suppose if you want to find L1 difference L2 means 3, 4 is common in both L1 and L2 language. So the remaining element in L1 is 1 and 2. So that is the difference. So I think it's clear. So L1 difference L2, it is similar to your mathematics. We can rewrite this L1 difference L2 equal to L1 intersection L2 dash is also regular. So here already we know if L2 is a regular language, then complement of L2 is also regular. We know that. Similarly, if L1 and L2 are regular, then intersection of L1 and L2 is also regular. So based on that, we can conclude here the difference of L1 and L2 is also regular here. Suppose if we find L2 dash means, after finding L2 dash, then we find intersection between L1 and L2. It will give the difference of L1 and L2 here. So closure under intersection complements implies closure under the difference here. So this is the next set theoretic properties. The next one is symmetric difference. The difference between the previous one and the symmetric difference is, in the previous one, suppose there are two sets A and B. So as I already explained, A minus B means whatever the elements common in A and B, we can remove that, and the remaining element in set A can be given in difference. But in symmetric difference, we have to find both L1 minus L2 as well as L2 minus L1. So after finding this difference, whatever the element remaining in L1 minus L2 as well as L2 minus L1, we can combine all the elements. I'll give one example. So A equals 1, 2, 3, 4. There are 4 elements in set A. and B equals 3, 4, 5. There are three elements in set B. So A difference B means in the difference between A and B, we have to remove the common elements. The common elements between A and B is 3 and 4. So we have to remove that, and whatever the remaining elements in set A, that is 1 and 2, that is A minus B, L1 minus L2. So 1 and 2 is A difference B, and L2 minus L1 means again we have to remove the common elements 3, 4, 5. It is 3, 4, 5 is in L2. So we have to remove 3 and 4 because these two are common elements between set A and B. The remaining element in set B is 5. So finally we have to take the union. So the symmetric difference between L1 and L2 is 1, 2 and 5. So this is the symmetric difference. This is one example for symmetric difference. So regular languages are closed under symmetric difference because they are closed under difference and union. So we have to rewrite the symmetric difference. This is like the formula. So this is the symmetric difference. Other than these set theoretic properties, so these are all remaining properties: closed under concatenation, closed under clean star, closure under reversal, closure under homomorphism, closure under inverse homomorphism. There are some properties or certain operation that is non-closure. This is also discussed here. So these five closure properties already we discussed in the previous video, that is closure properties of regular language. The same thing is explained here. So concatenation already we know, if L1 and L2 are regular language, then concatenation of L1 and L2 is also regular here. For example, X, it belongs to the language L1, and Y, it belongs to the language L2, means concatenation of X and Y. It is also a regular here. X followed by Y. That is L1 followed by L2. Next, closure under clean star. So if L is a regular, then clean star, that is a clean closure, L asterisk equal to, it does not contain element, that is empty string epsilon. So here the language is Wi belongs to L. So this is the language. The I may be vary from 0. That is there is no W, or it may be a 1, or it may be 2, or 3, anything. So that is the combination here. Maybe empty string epsilon or W1, comma combination of W1 and W2. So it may be any combination. If L is a regular language, then clean closure of L is also a regular here. Next property is closure under reversal. So if L is a regular, then L reversal of L is also regular here. So W is a regular language, then reverse of W is also a regular language. Already we discussed one example. For example, 10 is a regular language, means 01 is also a regular language. Reverse transition in non-NFA make accepting states initial and initial status accepting. Closure under homomorphism. So here the function we can write it as symbols to string. This is the input symbols, and this is the string we are going to use. So H colon sigma to star. If L is a regular, then H of L is also regular. One example we discussed in the previous video. Closure under inverse homomorphism is if L is regular, H is homomorphism, then H inverse of L. H inverse of L is inverse of inverse homomorphism. So W, this W, that is a homomorphism of W, that string that belongs to the language. So here in closure property, symbols to strings, we are using the symbols and we can make the strings there, but it is vice versa in inverse homomorphism. So what are all the non-closure under non-closure properties under certain operations, means these regular languages are not closed under subsequence operation and context-free intersection. So subsequence means, for example, if L equal to A to the power n, B to the power n is not regular, means finite automata can't count matching numbers. So here if it is not regular, means we cannot count how many number of A's and B's in this subsequence operation. For example, subsequence, it is like a substring only. We have to delete some characters. For example, A, B, C, D. This is the given string. Subsequence of this string, it may be AC. We have to delete B and D. So here it is not closure under certain operation. This is one of the operation, subsequence operation. The next one is context free intersection. So in context free intersection, regular language, regular and context free may not be context free. So these two operations, subsequence and context free intersections, are not closed under this operation. Thank you.